So when you're solving these equilibrium and compatibility problems, it'd be very useful to know these common boundary conditions that are often found in these problems. So typically we're talking about cases where you have transverse loading, so basically a force that's perpendicular to the beam length. So if you have a fixed boundary condition, like in the case of like a cantilever beam, at that fixed boundary condition here, you know that the or the distribution along the x-axis is zero at the origin or along the centroid of your cantilever beam. The displacement along the y direction is zero along from at x is equal to 0, and then also the change in the displacement with respect to x is equal to 0, or the slope is 0 at x is equal to 0. Okay? In a similar fashion, for a pinned boundary condition, we know that the displacement at our origin point is 0 in both the x and the y direction, and we know that the moment, because a pin can't apply a moment to the system, the second derivative of the y displacement must be equal to 0 at the origin as well. Okay. For a roller condition, a roller does not have a prevents displacement within the y direction, and it also, similar to the pin, can't apply a moment, so the second derivative with respect to x at the location of the pin must be equal to 0 as well. All right. So the last condition that you'll use for transverse loadings involves the equation for shear stress within a beam. So tau of xy. So if you have a transversely loaded beam, the shear stress distribution, so this is across, is going to be like parabolic in nature, where and it's going to be equal to VQ over IB. So V is the shear force, I is the moment of inertia, and B is the width of the beam at the point of the shear stress that you're calculating. So the only variable if you have a continuous cross-section beam is Q. So Q is the first moment of inertia, or first moment of area, and you can solve it using this equation here. So Q max occurs when y1 is at the centroid, but the thing that's most important for you to know is that at the edges of the beam, so this is at plus c and minus c, so when y is equal to plus c or when y is equal to minus c, q is actually equal to 0 because our integral would be from y max to y max. So we end up getting basically 0 in that case for q. Therefore, tau of xy would be 0 at the top and bottom surfaces of our beam. All right. So using that, you can then apply that boundary condition along with the boundary conditions at fixed pinned or roller constraints along your section, and you should be able to then hopefully solve. Use these to help solve for your displacement fields, u of xy and v of xy, for simple beam problems.